There are a few modified forms of the, or alternate forms of the definition of the derivative. So we're going to use this one right here to complete this problem. All right, this gives a numeric value. Okay, this way, if you're looking for one specific value rather than a function of the derivative, then this might be a quicker one to use. Okay, so f prime of 21, just plug in the blanks. So we're going to have f of 21 plus h. So instead of writing s, I'm going to write 21 plus h in there. Minus f of c. So what, if we plug in 21, 21 minus 5 is the square root of 16, which is 4, all over h. Alright, so we have the limit as h approaches 0 of square root of 16 plus h minus 4 all over h. I can't plug in 0 yet, but what I can do is multiply this by the conjugate 16 plus h plus 4. 16 plus h plus 4. Okay, looks like it's getting worse, but that means it's getting better. We'll have 16 plus h minus 16 all over h times this conjugate form. H's, the 16s will cancel out. The h's will cancel out, so we'll be left with the limit as h approaches 0 of 1 over square root of 16 plus h plus 4. As h goes to 0, we're going to get 1 over 8. And that's equal to f prime of 21. Alright, there's another form. This is the alternate form. It also gives a specific numeric value, not a function. So if you want a function as a derivative, then don't use this form. Alright, so for this one, f prime of 21 equals the limit as x approaches 21 of f of x minus f of 21 all over x minus 21. Okay. Plug in the values. Minus 4. Again, we can't just plug in 21, so we're going to have to multiply by the conjugate. Simplify. And on the numerator, you're going to see that this 5 and the 16 will combine to give you 21. So we'll have x minus 21 on the top, x minus 21 on the bottom. Those disappear. So we get the limit as x approaches 21 of 1 over x minus 5 plus 4. Plugging in the 21 now gives you 1 over square root of 16 plus 4, or 1 over 8. So you get the same answer, just a different way of doing it. Okay, and so now we have that idea of differentiability at a point. We can only take a derivative at a point if the slope from the left and the slope from the right equals some specific finite value. Okay, so the graph must be continuous. The slopes have to merge into each other smoothly. So if we have something like this slope could be -1, this slope could be 1, and then this would not be differentiable at that point because they don't go into each other smoothly. Okay, so just a good example to talk about this. This is that absolute value function, just move to the right 2. So we have this as our f of x. So is f of x differentiable at 2? It appears not to be, but let's use that definition. Okay, limit as x approaches, we'll say 2 from the left, and it's f of x minus f of c, but c in this case is 2, all over x minus 2. So we're talking about the limit as x approaches 2 from the left of absolute value, x minus 2, minus f of 2, which is 0, over x minus 2. Good thing we know about this function. Remember, that's just a piecewise function where it's negative 1 on one side and 1 on the other. So if we go on the left side of 2, where the numbers are lower, we're going to get negative 1. As we do this from the right side, it's going to be the same exact function, but our limit this time is going to be different. It's going to be positive 1. So we would say f of x is not differentiable. Nice long word. At x equals 2. All right. So then we are able to do something like this. Discuss the differentiability of f of x equals the cube root of x at x equals 0. So take the limit as x approaches 0 from the left of this minus 0, okay, over x minus 0. So we get the cube root of x over x. Well, that's really x to the 1/3 over x to the 1st. Okay, so I could write it as x to the 2/3 in the bottom. And x to 1 over x to the 2/3 is x, as we put in a 0 there, we can't have a 0 in the denominator. Okay, so this doesn't exist, or you can say technically infinity. It's going to be the same exact function if we look on the right side. So I'm going to skip a few steps here. This one also doesn't exist, or you can consider infinity. So f of x is not differentiable. Okay, and the cube root of x, if you know what that looks like, it's kind of something like this. And, well, that's not a very good picture. Your calculator will do a much better job than me. Okay, but the problem is the slope actually increases so fast right here that it's not differentiable. And you can look at that on your calculator. Now, this will be one of our last problems for today. Discuss the differentiability of that function. All right, so we have the limit as x approaches 0 from the left. Doesn't matter if we do the left or the right first. Okay, just to rewrite this so we have it. So we have the limit as x approaches 0 from the left of x to the 2/3 minus 0 over x minus 0. So that's x to the 2/3 minus x to the 1st, which will be x to the negative 1/3, or 1 over x to the 1/3. And this is going to be, as we look at 0 from the left, it's going to be another does not exist, or negative infinity in this case. So because of that, f of x is not differentiable. That's a long word. If you write something like this, I'll understand what you're saying. Okay, at x equals 0. And investigate what the graph of this looks like. I believe it's the seagull shape, but I'm not 100%. You have to check it out. Down here we have some very important theorems. So if a function is differentiable, then it is continuous. Okay, it doesn't work the other way around. If it's not continuous, however, then it's not differentiable. So what I would like you to do in your WISC for tonight is to summarize specific cases when a function will fail to be differentiable. Okay, we've seen 3 different cases, and I'd like you to mention those in your WISC. Do a couple practice problems, have